Hello again. This is Elijah Craig with the Physics 2212 Lab 2 Lines of Charge video lab report. The background for this lab is similar to the background from Lab 1. We know that objects can require a net negative or net positive charge just by rubbing them together, pulling them apart, or just touching other objects. We also know that any charge must be between the charge of an electron, 1.6 times 10 to the negative 19 coulombs, and the net charge if every electron was removed from that object. In Lab 1, our goal is to determine the charge in coulombs of one piece of charged tape. We have the same goal in Lab 2, and we determine this by finding the force of gravity on one piece of tape and then putting it in static equilibrium, meaning there's no net force, and balancing the force of gravity with the electric force from another piece of tape. And in Lab 1, we assumed that each piece of tape could be treated as a point charge with all the charge in the center of the piece of tape at one point. We also assumed that each piece of tape had the same net charge. So here you can see a diagram of how we found the electric force. We found the distance between the two pieces of tape when um, the top tape was in static equilibrium. And in this experiment, the distance was about 1 inch or 0.0254 meters, which is the same distance we will use in our computational model for Lab 2. In Lab 1, when we were treating each piece of tape as a point charge with all the charge at that center of the tape, we found that the total charge of one piece of tape was 1.218 times 10 to the negative 8 coulombs per piece of tape in order to achieve static equilibrium with the force of gravity. In order to use these models, we needed some basic understanding of physics principles. The first being Newton's second law, which is force is equal to mass times acceleration, where we used our mass of one piece of tape of 0.000218 grams, and our acceleration of g, which is equal to 9.81 meters per second squared. We also needed knowledge of math through the distribution of charges, where we can model the distribution of charges as equal individual charges spread over the area of the object, and these can be added up in order to find the net field from the whole cluster of individual charges. For Lab 2, we are assuming that all the charges on the tape are evenly distributed over the surface of the tape, and the total charge on both pieces of tape is equal in both sign and magnitude. We are also ignoring air resistance in the force calculation, and we are using a force due to gravity of our mass 0.000218 times g, which is 9.8 meters per second squared. So here you can see the first part of our computational model, where we've created 15 equal charges for each piece of tape. So we have two lines of charges. One is labeled as dq top, the other is labeled as dq bottom. And this function is taking the field on each charge on the top line, or dq top, and calculating the field on each section caused by the charges on the bottom tape, dq bottom. Here's the result of our computational model after we multiplied the field on each top charge by the charge of that dq, or that top charge. That gave us the resulting electric force on that charge itself, and then the sum of these charges yielded our net force, or net electric force. So the green arrows in the model here are all of the individual forces on the top piece of tape, and the big white arrow is the net electric force, which is equal in magnitude and opposite in direction of the yellow arrow, which is the force due to gravity. And we found the electric force and balanced it with gravity by manipulating the initial total charge of the tape in order to find the total charge of the tape. So through this new and current model with distributed charges, the net charge of a single piece of tape was calculated to be 2.69266 times 10 to the negative 8 coulombs. which our original value again was 1.218 times 10 to the negative 8 coulombs. And the difference between these two values can be explained by a lack of precision in the point charge model. Modeling as a point charge neglects the effects of the charges on most of the area of the tape, and it neglects the difference in field on the center of the top tape by charges on the bottom edge of the bottom tape. So we can assume that the model with distributed charges is likely closer to the real charge of this tape.